There are two types of GABA receptors, ionotropic and metabotropic. Ionotropic receptors are receptor channels, but metabotropic receptors are not receptor channels. We are going to study the GABA-A receptors, which are ionotropic receptor channels. The GABA-A receptor channel is made up of 5 subunits. Here on the right, you have the general organization of a GABA-A subunit with a large terminal NH2 terminal domain, 1, 2, 3, 4 transmembrane segments, and a C-terminal domain, which is also extracellular. These subunits are called alpha, beta, or gamma. There are also other subunits we are not going to study here. On the left here, you have 2 examples of GABA-A channel, GABA-A receptor channel, one with 2 alpha subunits and 3 beta subunits, and one with 2 alpha, 2 beta, and 1 gamma. And the receptor site for GABA is located at the interface between 1 alpha and 1 beta subunit. So we see here that we have 2 receptor sites for a GABA receptor channel, and for this one too, it's always like that. There are 2 receptor sites for GABA. 2 molecules of GABA bind to the GABA receptor channel for this channel to open. So we can write it like that. 2 molecules of GABA and here the receptor in the closed state, the GABA receptor in the closed state, must bind to the receptor, which finally opens. This is the open state with the star. And then it closes back when GABA unbinds from its receptor sites. Which type of ions cross the GABA channel? To address this question, we record the unitary GABA current. We record in cell-attached configuration to record a single channel activity, and we record in voltage clamp mode to record a current. In this configuration, cell-attached, the pipette solution corresponds to the extracellular medium because it's extracellular to the recorded channel. So in this pipette, we add the extracellular concentration of sodium, potassium, of chloride, here 146 millimolar, and we add also GABA to open the GABA channels. And we hold the membrane potential at minus 60 millivolt and we record no current. If we hold the membrane potential at minus 30 millivolt, we record an outward current. At 0 millivolt, we record an outward current but larger. And at plus 20 millivolt, we still record an outward current and larger again. I want to remind you that an outward current corresponds to an exit of positive charges or an entry of negative charges. And to understand the type of ions that carry the GABA current, we are going to do, as usual, the IV plot. Why? Because when we identify the reversal potential of the GABA current, it will give ideas on which type of ions are involved. The corresponding IV curve, which is the unitary current of, here it's unitary current of GABA, versus membrane potential, we see that the current is outward. This is what we have here, and more and larger when we depolarize the membrane. And now we have the impression that the current reverses at minus 60 millivolts. Here, the possible reversal potential of the GABA current is minus 60 millivolts. This suggests that chloride ions are involved. If this hypothesis is right, do chloride ions go in or out in the situations that we have studied here? Let's have a look. Chloride ions, due to the concentration gradient, have a tendency to enter the neuron. And at, for example here, plus 20 millivolt, when the membrane is more positive on the inner side than on the outside, of course chloride ions have also a tendency to enter due to the electrical gradient. Negatively charged ions are attracted by positive charges of the inner side of the membrane. So the net flux is an entry of chloride ions. An entry of chloride ions is an outward current of plus charges. And it's exactly what we record. So it seems that our hypothesis that chloride ions are involved, and maybe the only ions involved, is possible. To address this question and to get a definitive answer, we are going to change the chloride concentrations on either side of the membrane. So this is here the previous situation with physiological concentrations of chloride ions. And on the right now, it's what we call equivalent chloride. So we have the same concentration of chloride inside and outside. So there is no concentration gradient. There is only an electrical gradient that forces the ions, the chloride ions, to move. And the equilibrium potential for chloride ions is 0 millivolt. And what we see here, if we redo the IV curve, so I remind you that this is the unitary GABA current with a lowercase I versus membrane potential, so it's a holding potential. We see that it reverses around 0, which fits with the hypothesis of chloride ions, and it's inward for hyperpolarized potentials and outward for depolarized potentials. And why? Because now the chloride ions follow the electrical gradient only, and when the membrane is more positive on the inner side, the chloride ions will have a tendency to enter, so it corresponds to an outward current of plus charges. We have it outward, positive current is outward, and the contrary, of course, for hyperpolarized membrane potentials.